All right, so in our data booklets, we're looking at the table of water vapor pressures at the back of the book, page 14. On your paper, can you just sketch for me what a graph would look like if we made a graph using this data? So sketch what the graph should look like if we took the data there and just graphed it. The first column would be our x-axis, the second column would be the y-axis. So if you made a graph of vapor pressure versus temperature, what does that look like? The answer is what? It should look like, what's the name of it? Anybody?
Exponential?
That's what we're looking for. It would be an exponential function, an exponential shape, which means it starts off very low and then suddenly it shoots way up, right? That would be the graph you would expect to see for vapor pressures versus temperatures. If you went to the y-axis and you picked standard pressure, let's suppose this was in atmospheres. If you picked one atmosphere and you went right across to the curve and straight down, what would that number be if this was water?
The normal boiling point.
Without
100.
looking in your data booklet, that would be 100 degrees Celsius, wouldn't it? Why is that? Because that's the normal boiling point of water. That's the temperature when water's vapor pressure is the same as standard pressure, right? So without even looking in my data booklet, I know what water's normal boiling point is. I should have been able to say that. Now, Clausius Clapeyron, we learned yesterday, and again, I'm probably mispronouncing that. He graphed, or they, I'm not even sure if that's two people, they said if you have this exponential graph, you can tame it, you can make it linear by graphing the natural log of vapor pressure versus the reciprocal of Kelvin temperature. And they said this would create a falling straight line graph. They gave us an equation. The natural log of vapor pressure is negative delta H vap, the heat of vaporization, over temperature, over R, times 1 over temperature, plus a constant. That was the Clausius Clapeyron equation, which, by the way, do you notice that this is on your data booklet's formula sheet? It's on the bottom right-hand side of the formula sheet at the front of your data booklet. So y is equal to mx plus b. If you graph natural log of vapor pressure on the y-axis, reciprocal of Kelvin temperature on the x-axis, it should look like a straight line. And the important thing is that the slope of this line gives you negative delta H vap divided by R. So let's quickly review what we did yesterday. I want you to take your calculator, take the data booklet, and pick any 6 random points. Make sure they're not all close together. Make sure they're kind of spread out. 6 random points from the table that's there for water's vapor pressures. And we're going to enter them and we're going to construct that graph that we just described. So how do I do this? I'm going to assume once we've done this 2 or 3 times, I'm going to assume that everybody knows how to do this and it would be a fair test question to give. So how do I enter the data? Someone tell me what to do.
Go to stat and press 1.
So stat and choose edit, the first one. If I have some numbers already there, what do I do?
go to the L number of the one you want to clear, and then
So
press
put-
clear and then enter.
Yeah, so put the cursor on top of the list symbol, press clear and enter. What happens if you just press clear and enter without putting it on the L symbol? So if I push clear and enter, nothing happens, right? Suppose I wanted to change one of these numbers. I just wanted to change one because I typed it in wrong or something. There's a delete button, isn't there? You can delete something, DEL, right above the stat button. Or I think you could just start typing over a number that's already there, right? You just type over it. Anyways, delete whatever numbers you have. And then randomly select 5 or 6 temperatures, put them in the first list, and randomly select 5 or 6, well, not I guess no longer randomly, select the pressures that go with your temperatures and put them in the second list. So do that real quick, and do not choose 5 or 6 that are right close together. Make sure they're spread out. And I hope you guys are able to generalize, right? What we're doing here with Clausius Clapeyron, you could do this for any data, right? If you had data in some science experiment or a math class or a lab you had done, you could make a graph of your data directly on your calculator, couldn't you? Using this technique. So you've got your numbers hopefully entered already. You've got temperatures in the first list. You've got pressures in the second list. Now, to make our graph, we don't want Celsius temperature on the x-axis. What do we want on the x-axis?
Kelvin temperature.
Kelvin temperature.
No. Listen more carefully. On the graph we're about to make, what are we going to plot on the x-axis?
The reciprocal of Kelvin
Thank you.
temperature.
Yes, we're going to plot the reciprocal of Kelvin temperatures. There are several ways you could do this, but here's a way to do it in just one fell swoop. What do you do with your cursor? You put it on
Over
top.
L1.
Yeah, well, not on L1. Put it on top of the next available lists symbol. So put it on L3. So at the bottom of your screen, it says L3 is equal to, as though you're going to type a formula. So how do I, right now, where are my temperatures? They're in list 1, and those are Celsius temperatures. So I have to do 2 things, don't I? I have to convert them to Kelvin, and I have to take a reciprocal. I could do that in 2 different lists. I could make this list converting them to Kelvin, and I could make the next list doing the reciprocal. I could, but I can also do it in just one step right here, a reciprocal. There's more than one way to do that, but 1 divided by is a simple way to do it. 1 divided by the temperatures, but they have to be converted to Kelvin. So what should I type now?
L1 plus 273.15
Almost.
in brackets.
Yes. Okay, it has to be in brackets. Otherwise, the calculator would go 1 divided by list 1, and then it would add 273 to that, right? So you want to go 1 divided by L1 plus 273 in brackets. Order of operations, the brackets would get done first, and then the reciprocal. Press enter. And do these numbers make sense? If you convert those Celsius to Kelvin, won't they be big numbers? 270, 280, 370, right? They're big numbers. And when you take the reciprocal of that, you get very small numbers, don't you? So these make sense. Now go to list 4. If list 3 was the reciprocal of Kelvin temperature, which was on my x-axis, what's going to be in list 4?
The natural log of the pressure.
Very good. The natural log of the vapor pressures, right? So let's put our cursor up on top of the L4 symbol. The bottom of the screen, L4 is equal to, and the natural log is what button on the calculator?
LN.
LN. Why is it LN when it's a natural log?
Because of its French name.
That's right. It's the French. It's logarithme naturel. So LN is natural log. So you say it's simply the natural logarithm of the vapor pressures. So natural log of what?
L2.
L2. And press enter. What does it mean to say the natural log of 4.6, the first value of L2, on my values, is 1.5? What does that mean? That the natural log is, or any log, is what? What was my definition of a logarithm?
Exponent.
It's an exponent.
It's an exponent. So what's the base for a natural logarithm?
10.
E.
No, the common logarithm. If you just say log, L-O-G, that base is 10. What's the base of the natural logarithm? I think I just heard it.
E.
It's the number E, which you probably just heard first time yesterday. E is like pi. Pi is 3.14, etc. E is around 2.7. So what is the natural log of 4.6? It's the exponent that 2.7 E would get raised to give you 4.6, right? If you take 2.7 and raise it to the power of 1.5, you'll get an answer pretty close to 4.6, right? That's what the natural log is. It's the exponent that the number E gets raised to give you that pressure, 4.6. All right, we're ready to make our graph. Can I just point out, if all we want is the slope of the graph, if that's all I want, I don't really need to make the graph at all. I can just do linear regression right now, right? But let's see what the graph looks like. What do I do? How do I see the graph?
Zoom 9.
Well, that's the last thing I do. What do I do first?
Stat plot.
Yeah, I got to set up the graph, don't I? So I go to stat plot, which is right above the y equals button on the calculator. So second function, stat plot. Why stat plot? Because we're trying to plot the numbers we just put in the stat menus, didn't we? Stat plot. It's to make scatter plots. Now, you can see on my calculator, 2 of them are turned off and 1 of them's already turned on. So I might as well use the one that's already on, right? If none of them were on, then you can use any of them. If more than one of them is on right now, you should turn all of them off except for one. So go to the one that's turned on. If you want to turn it off, you just go to the word off and you press enter, right? Now it's off. Put it over the word on and press enter. Now it's on. You can make different types of graphs. The first type is the scatter plot, right? The second type is a line graph, then a bar graph, then box and whisker plots. I have no idea what that last one is. In any case, X list is what do you want to put on the x-axis? And for us, that's reciprocal of temperature, isn't it? Which was in list 3. So your X list should say L3. Change it if it doesn't. On the y-axis, we're plotting natural log of vapor pressure. So therefore, that's list 4, where I did that. You notice when I talk about it, I don't just say list 3 or list 4. I say what it means. It's the reciprocal of temperature. It's the natural log of vapor pressure. Don't just focus on the calculator. Focus on what the calculator's doing for you. It's making this graph for us. Now I'm ready to do what I think was Max or Devin, I'm not sure who, zoom number 9, zoom stat. What does this do when I press zoom stat? It sets the window settings to automatically show me the graph. That's what zoom stat does. number 9. And I'm happy with what I see.
Why is there a line on my graph?
If you remember, we did this yesterday, and yesterday we did linear regression, and we stored an equation yesterday. So if you press your y equals button, you probably have an equation there from yesterday. That equation is being plotted right now. So just clear it. Press clear to get rid of that equation. Then go back to your graph, and now there should not be that line.
Got it. Thank you.
Okay, so now we want to get the slope of the line, right? That's linear regression. So how do I do linear regression?
You go to the vars thing.
Nope.
You go to stat.
We go to the stat menu, stat button. And then where?
Calc.
We go to the calculate things. And which of these do we want to do?
Lin reg.
Yeah,
Or
you notice there's also one down at number 8, and I honestly don't know why they offer these two. I don't know, other than one says ax plus b and the other one says a plus bx. I'm not sure why you would offer both of those. But anyways, we use number 4, lin reg. If you have the newer calculators, you tell it where your x list is, you tell it where the y list is. And again, if all you need to do is get the slope, then that's all you need to do. You could say calculate. But if you want to graph it, if you want to see the graph, then you go to the store regression equation after you've said L3 and L4, the x's and the y's. And now I try to tell it to store the equation as function y1, right? So how do I do that? I go to this is where we go to the variables, the vars, and then we go to the
y vars and function.
y variables, and then we choose functions. And you could use any of these. If you already had an equation in y1 and you didn't want to lose it, then you'd say y2, right? That's why you can do different ones. For us, we don't usually care about old equations, so we'll just say y1 and calculate. Does anybody have the older calculator and want me to do that one? No?
Yes, please.
Okay, real quick. So on the older calculator, it's almost the same. So we go to the stat menu, we go to calc, we choose lin reg, linear regression, but we don't get that menu that they saw the newer calculators. So now what we do is we say the X list was L3. Then we put a comma, and the comma is the button right above the number 7 on the keypad, this comma button. You put a comma, then you say where the Y values are, list 4. So you're doing the same thing, but in a slightly different way. And then if this is all you want is just to get the slope, you could press enter right now and it would work. But if you want to see the line, you put another comma, and then you do that variables thing, the vars button, the Y variables and the functions, and you say Y1. So now you're saying, take the data in list 3 and list 4 and do linear regression. Take the equation you get and plot it as function y1. Press enter. And I don't have any data, so I get an error message, but you'll see you get essentially that same kind of information that we had before. What do I want from this screen?
The A value,
Which we would say is,
the slope.
but what number would I write down? Do I write all of that down?
No, only like the first 4 digits.
Even the first 3, because think of those pressures and temperatures. How many sig figs were in there? Like, do we need 4 significant digits even? So my slope was negative 5,200. So I'm going to go to my graph here, and I'm going to say for water, the slope is negative 5,200, your slope could be different because you might have used different points than me, right? But it should be similar to that. And looking up at Clausius Clapeyron, the slope was negative delta H VAP over R. So let's say that this is negative delta H VAP. Now, which R do we use? Which gas constant do we use? Anybody?
Atmospheres.
No, we want the SI version of R, the one that's going to give us joules.
8.314.
8.314.
8.314, which is the SI version for R. If you'd forgotten that that's the SI version, you should remind yourself there. So to get delta H, you can do it in two ways. You could start by saying, hey, the two negatives just cancel. Okay. Or you could not do that and just say negative 5,200 times negative 8.314. This morning, there were some people that didn't seem to understand. If you have a fraction and you say negative 2/3, you can put the negative out front like that and say negative 2/3. You can put it on top and say negative 2/3. You could put it on the bottom and say 2/-3. Those are all the same things, right? So when we normally put Clausius Clapeyron, we put it either out front or on top, but you can put it on the bottom and it's the same thing. So what I'm going to do is think of it as being on the bottom and say negative 5,200 times negative 8.314. That's going to give me delta H VAP. A negative times a negative will be positive. Delta H is not always positive, but delta H VAP is. Delta H VAP is the energy needed to vaporize the liquid. You got to put energy in to vaporize a liquid. So that means delta H VAP is always a positive number. It's endothermic. If you have a negative delta H, it's exothermic. So this 43,200, I'll just keep 3 digits, and it's energy, right? It's heat. So this is joules per mole, right? Everybody remembers JOULES. Those are the units for energy, SI units. Divide that by 1,000, 43.2 kilojoules per mole. Your answer might be slightly different, but it should be very similar to that.
Mr. Patnode,
Yes.
could you explain how you got to the 43,200 part again?
So go to the side of your paper and say 2 equals 6/3.
Okay.
We're looking for delta H, which is like looking for the 6, isn't it?
Yeah.
2 times 3 is 6.
Oh, okay.
So negative 5,200 times negative R will give me delta H.
All right. Thank you.
You're welcome. All right. This is the graphing version of Clausius Clapeyron, and it's the most accurate version because it uses a whole bunch of data points. What we're going to look at now is I'm going to call it the 2-point version of the Clausius Clapeyron equation. This is not as accurate, but you don't always have 6 or 7 or 8 points. Sometimes you do just have 2 points. You have 2 pressures and 2 temperatures. So what do you do then? Making a graph out of 2 points is kind of dumb, although it's very linear, isn't it? How come no one ever laughs at that? That's a very good math joke. If you make a graph out of 2 points, it's very linear. Oh, dear God. Okay. Suppose you have a P1 and a P2, a T1 and a T2. According to Clausius Clapeyron, the natural log of P2 would be negative delta H VAP over R times 1/T2 plus the constant. The natural log of P1 would be negative delta H VAP over R times 1/T1 plus the constant. Let's take those two equations and subtract them. If you subtract them, you get the natural log of P2 minus the natural log of P1 on the left. Now on the right, do you see something, little tiny nice thing that's going to happen here? Anybody you see something nice that will happen when I subtract? Nobody?
Won't they cancel out? Like
What will cancel?
the C's will cancel out the
The
constant.
constants will cancel, right? C minus C, it's going to be con, right? So what we'll be left with is negative delta H VAP over R times 1 over T2 minus negative delta H VAP over R times 1 over T1. The constants will cancel out. Now, we're going to clean this up, but before I clean it up, let me take a little bit of an aside here. There are rules for powers. You learn them in grade 9 math, right? If you take a power and multiply it by another power and they have the same base, you keep the base and you add their exponents together. If you have a power and you divide it by another power with the same base, you keep the base and you subtract their exponents. And if you have a power raised to another power, you keep the base and multiply their exponents. So there are these simple rules for powers. But logarithms are just the inverse of powers, right? We saw that yesterday. The logarithm, it comes from powers. So if there are power rules, there's going to be log rules of a similar form. One is the product rule. If you take the log of a product, two numbers multiplied, let's say m times n, that will equal the sum of the logarithms. So the log of m plus the log of n is the same as the log of m times n. I can illustrate that rather easily. If you say the log of 1,000, well, that's the same as the log of 100 times 10, isn't it? But according to this rule, a log of 100 times 10 should equal the log of 100 plus the log of 10. When I write log, the base is 10, right? So the log of 1,000 is 3. So log of 1,000 is 3. The log of 100 is 2, because 10 squared is 100. And the log of 10 is 1, because 10 to the 1 is 10. 3 is equal to 2 plus 1. Yes. So that rule works, right? If there's a product rule, there's probably a quotient rule, isn't there? The log of m divided by n. What would that equal? Can someone guess what that will equal?
Log of m minus log of n.
Very good. We're going to use that rule when we go back to Clausius Clapeyron. The third rule is very powerful. This one's actually quite useful. The log of m to the power of some other exponent, let's say m to the x. According to log rules, you can then say that that's equal to x times the log of m. Just to show you what an example of that, when we had a minute ago log of 1,000, that's the same as log of 10 cubed, isn't it? Well, according to this rule, the log of 10 cubed should be the same as 3 times the log of 10. Is this true? Well, the log of 1,000 is 3. The log of 10 is 1. Is 3 equal to 3 times 1? Yes, right? I claimed that that's a very useful rule. The old math teacher in me feels I cannot leave this without an example. Suppose I gave you an equation that said 8 to the power of 2x plus 5 equals 4 to the power of 3x minus 1. Could you solve that? Yes or no? Anybody? Is that easily solved? Yes or no?
No.
Does anybody think that's easily solved?
Yeah.
Take the log of both sides.
And no, don't go there. Okay? Don't use any logarithms. This particular example does not need any logarithms. Does anybody know what I would do with this?
Put it in the calculator.
No. No. What
Make their bases same.
Very good. What makes this easy is that 4 and 8 can both be written as powers of 2, can't they? So this is 2 to the power of 3 to the power of 2x plus 5. And this is 2 to the power of 2 to the power of 3x minus 1. When you have a power raised to a power, you can multiply their exponents. So this is 2 to the power of 3 times 2x plus 5. And this is 2 to the power of 2 times 3x minus 1. Now, if I have two powers that are equal and they have the same bases, then their exponents must be the same, right? So therefore, you can just say 3 times 2x plus 5 is equal to 2 times 3x minus 1, and you're finished. That's easy to finish solving, right? So what made that simple is that the bases in the original equation could both be written as powers of 2. But what if you had a question where that was not possible? 5 to the power of 3x plus 4 equals 7 to the power of 2x minus 1. You can't play that trick anymore because 5 and 7, you can't write them as powers that are with the same base. But now you can do what Erica was going to say. You can use that log rule that we just said. You can take the logarithm of both sides. The log of the left side equals the log of the right side. Now, at first, you'd say, why the hell would you do that? It looks even worse now. But wait, the log of 5 to the power of this would be, according to that last rule, 3x plus 4 times the log of 5 equals 2x minus 1 times the log of 7. Do you see what we've just done there? Those variables used to be exponents, and therefore they were, impossible. You couldn't solve that. But they're no longer exponents. Now they're just multiplying. Log of 5 is a number. I could grab my calculator and tell you what log of 5 is. It's just a number. Log of 7 is just a number. So now I could multiply through my brackets and I'm home free, right? So that's a very good trick to have, especially if you do a lot of math contests. This kind of equation shows up on math contests a lot. Coming back to Clausius Clapeyron, look at what we have on the left-hand side there. Natural log P2 minus natural log P1. Wouldn't that be natural log of P2 divided by P1 according to the second log rule? Good. Equals, on the right-hand side, well, it's messy, it's ugly, but aren't there just two terms here? There's this ugly term minus this ugly term. And when you look at those two ugly terms, don't they have something in common? We can't cancel it out. Please don't say that. But when you have two terms like that and they have something in common, can't you factor it out? We can factor negative delta H VAP over R to the front and just say it's the same as the reciprocal of T2 or times the reciprocal of T2 minus the reciprocal of T1. So there is the 2-point version of Clausius Clapeyron. If you look in your data booklet on the formula sheet on the bottom right-hand side, you'll see that this is written right next to the original version of Clausius Clapeyron. A couple of things to note before we use the equation. When I derived it, I started with natural log P2 on top. I didn't have to. I could have started with natural log of P1 on top, which means this could equally say P1 over P2. But then in the brackets, what would it say? Instead of T2 here, it would be T1, and over here, T2. So you can switch these two pressures as long as you also switch these two temperatures. The second thing to note is that some textbooks will take this negative symbol here and they'll put it into the brackets, right? A negative sign out front. You could just move it into the brackets. That would make this guy negative and it would make this guy positive, which means they would just trade places. So some books will say positive delta H VAP over R, and then inside here would be T1 reciprocal minus T2 reciprocal. So in the end, here's my message to you. You could see this equation in forms that don't look like this. You might think, oh, there's a mistake. No, there's no mistake. It's just algebraically manipulated to be slightly different, okay? So if it doesn't look exactly like that, don't think there's something wrong. It's just written in a slightly different way. You may not be able to see why, but trust that it is. Okay, let's try a couple of questions. First, we're going to try 3 questions if we can get them in before 3:30. So the first question, there are 3 things in this equation. There's pressure, there's temperature, and there's delta H VAP. Let's find delta H VAP. So number 1, calculate delta H VAP for water using vapor pressures in the data booklet. But we've already done this. We've made a graph. Yes, we did. And that graph gave us a very good estimate of delta H VAP, 43.2 kilojoules per mole. But now we're going to do it using only 2 points from the data booklet. So go to your data booklet, look at your vapor pressure chart, and pick 2 points, but don't pick 2 points right close together. Pick points that are kind of far apart from each other. Any 2 points, and write them down on your paper. So I'll use 10 degrees Celsius. This is going to be my T1. My P1 would be 9.2 millimeters mercury. My T2, I'll go somewhere further to the right. My T2, what the hell? I'll use 70 degrees Celsius. And my P2 is going to be 233.7. Please don't just use the same as me. Use different values. So based on these 2 points, we want to know what delta H VAP is. So look up at your equation, plug your numbers in. So natural log P2 over P1 equals negative delta H VAP over R times. The graphing calculator has a nice button for doing reciprocals, this little x to the -1 button. So rather than say 1 over T1, I'm going to say, or sorry, 1 over T2, I'm going to say, where was it? I'm going to say, I've got to convert that to Kelvin, right? So 273 plus 70 is 343. So 343 reciprocal minus 10 degrees Celsius converted to Kelvin would be 283 reciprocal. So notice something, folks. The pressure that's on top should be paired with the temperature that was first, right? So you want to make sure you put them in the right places. It was a P2 over a P1. It was a T2 minus a T1. So make sure you're putting them in the right places. All right. Looking at this closely, I'm going to
each one.
I beg your pardon?
Why is there a negative exponent over the two numbers?
To raise something to the power of -1 is to take the reciprocal of it, isn't it? If you say in a
I
math,
guess.
you guess, I'm shocked that somebody in May of grade 10 advanced doesn't know that x to the -1 means 1 over x. I'd be very surprised if someone at this point doesn't know that in their math class. To raise
Hey,
something to
classmate.
the power of -1 is to take the reciprocal of it. Folks, are there people out there who honestly don't know that? Yes, no? Okay, so we do all know that?
I have another question.
Yes.
Actually, I have to leave early today, so is it okay if I leave now? Do
You
you
don't have
post the recording later?
You don't have to ask, Sarajana. Okay.
Oh, okay.
Have a good day.
Thank you.
I'll be posting this
You too.
on YouTube. Okay.
Okay, thank you.
Mr. Patnode,
Hello.
why is it like that? I know the 8.314 is
Yep.
like SI,
Yep.
the one that we're supposed to use, but why is it that even when the pressures are in milligrams mercury, why can we use that one?
Okay. So yesterday I made a claim without any proof, just a claim that the pressure units didn't matter when we graphed the equation because they didn't affect the slope. I made that claim, but I didn't prove it to you. I said it doesn't affect the slope, but clearly when you changed the pressure units, something has to change. What changes is the constant at the end. So if you used a different pressure unit, you'd get a different line, but it would have the same slope. It would have a different y-intercept, but it would have the same slope. Because it has the same slope, delta H VAP will be the same, no matter which pressure units you used. Okay, now I didn't prove that, I just claimed it. Over here in the 2-point version, it's actually easier to see why it doesn't matter. Because in the 2-point version, inside the natural logarithm, it's a P2 divided by a P1, which means the pressure units cancel, don't they? So if I use millimeters mercury and you used atmospheres, wouldn't the ratio be the same?
Yeah.
Because again, the units cancel, right? 1 atmosphere divided by 0.5 atmospheres is 2. 760 millimeters mercury divided by 380 millimeters mercury is 2. So you get the same ratio, right? No matter what units you use. So this is a simpler way to see why the pressure units actually don't matter as long as they're the same.
Okay, thank you.
Okay. All right. Now, folks, I'm going to just pick up my calculator and get the answer to this in one fell swoop. To understand how I'm going to do that, you have to look at this equation in the following way. I'm going to start over here on my calculator and type that in. That's one term. Then I'm going to multiply it by -r. Then I'm going to divide by these brackets. Can you all agree that in the end, I'll have delta H VAP by itself? If I take the natural log term on my calculator and multiply by -r, and then divide by these brackets, delta H VAP will be by itself. And I've got my answer. So here we go on your calculator. The natural log of, put in your own numbers for me, 233.7 divided by 9.2, close the bracket. Don't press equals or anything, just type that in. Now that I've closed the bracket, times by -r, and be sure you're using the negative symbol, not the minus sign. And then divide by those brackets. So open brackets, 343 reciprocal minus 283 reciprocal, then close the bracket, equals. My answer is very similar, but not the same as we got before. delta H VAP using my 2 points, 43,500 joules per mole. If you used different points, you'll get a slightly different value for delta H VAP, but it should be very similar. 43.5 kilojoules per mole. Okay. If you imagine that graph that we had of natural log vapor pressure and 1/T, imagine the points were not perfectly linear. Suppose they were linear, but there was a little bit of error in them. Okay. The first method where we graphed it, we ended up finding, whoops, that's a horrible line. We ended up finding the slope of a line. That was the best way to do it because the line uses all the points. Suppose somebody used the second and third points, just the second and third points, then they get a slope like that. Their slope is different from the best fit slope. If somebody used the third and the fourth points, their slope would be different again. So when you just use 2 points, it's not very good. When you use a whole bunch of points and get the average sort of, that's the best way to do it. So the 2-point version is less accurate. But of course, I don't need a graphing calculator to do this. I can do this with just a normal calculator and a piece of paper, right?
Mr. Patnode?
Yeah.
I got a number that was like way off of what you had.
Well, then I'm going to guess you
Yeah,
did
same.
something wrong.
All right, well,
Is that a good guess?
it's probably a good guess.
Let me start by checking. Look at your pressure on top. Does it match with the first temperature over here?
Yeah,
Did you switch temperatures to Kelvin?
yeah.
All right, so let's grab your calculator. Tell me what you're typing. Natural log of,
Of the
tell me what
P-
you're actually typing.
Oh, my numbers?
Yeah. And do it
21.7.
yourself, then do it yourself too. Natural
Yeah.
log of what?
21.7
Over.
over 13.6.
So you chose 2 points that were very close together, right? It's not the end of the world, but I asked you to choose points that were far away from each other. Okay, but it's not the end of the world. Then what do I do with that?
Multiply by negative 8.314.
So times by negative 8.314. And again, you use the negative symbol, not the minus, right?
Yeah.
And then what?
And then
Divide
divide by the 2 temperatures.
And tell me what the first divide by the 2 temperatures?
I mean, divide by the T2 minus T1.
No, but they're reciprocals, aren't they?
Yeah, yeah.
Okay, so what was your first temperature?
297.
Let me just double check that. So that was 23.5, 273, 290. Yeah, okay. 297 reciprocal, right?
Yeah.
Minus, what's your second temperature?
289.
Okay, 289. Your second point was 13.6. 16, 280. Yeah, that looks right. 289 reciprocal, right?
Mm-hmm.
Equals.
Oh, okay. I guess it is. I don't know what I did wrong before,
So
but now
41,700.
right.
Okay, so 41.7.
All right. Thanks.
All right, are we all good with that, folks? Question 2. Let's find a pressure. Calculate PVAP at, I'm going to choose a temperature that's not in your data table. How about at 45 degrees Celsius? Look at your data table in the data booklet. At 40 degrees Celsius, we're at 55 millimeters. At 50 degrees Celsius, we're at 92. We're calculating at 45 degrees Celsius, so I'm anticipating it's going to be around 70 or so, right? But let's calculate it. So natural log of, well, actually, before I do that, let's list our points. The pressure I'm looking for, I can call it P2 or I can call it P1. It would be slightly easier to be looking for P2 because it's in the numerator. So I'm going to let P2 be the thing I don't know. I need a P1, so I can use any point. I'll use the same point I used before, 9.2 millimeters mercury. By the way, do I know a P1 and a T1 without even looking at a data table for water? Do I know a pressure and a temperature for water without even looking in the data booklet? Yes, I do. And so do you. What pressure and temperature do we all know for water?
100 degrees Celsius is 760 millimeters mercury.
Very good. We all know water's normal boiling point. So at 100 degrees, the vapor pressure of water is 760, right? So I don't even need the data booklet. I could have used that as my P1 and T1, right? In any case, my T2 is going to be 45 degrees Celsius. My T1 is going to be, just like before, 10 degrees Celsius. 273 plus 45. This is 318 Kelvin. This is 283 Kelvin. Let's plug stuff in. Well, actually, let's write down one more thing. Delta H VAP. Rather than use the one we just calculated, let's use the one we got from our graph, 43.2. It's more accurate. So we'll say 43.2 kilojoules per mole. All right, so let's go calculate P2. The natural log of P2 over your other pressure is negative. Now be careful here. Delta H VAP was 43.2 kilojoules per mole. What do I write? Negative what? Somebody. Thank you. 43,200 joules per mole, right? When you're calculating delta H VAP, it comes out as joules. So when you put it back in, you got to put it back in as joules into the equation. You can't put kilojoules. The R is 8.314. Be careful here. The temperature that it goes first is the one that goes with the numerator over there. So I want 318 reciprocal minus 283 reciprocal. This is harder when you're new to logarithms. It's harder because the thing I'm looking for is trapped inside the logarithm, right? It's the natural log of P2 over 9.2. The thing I'm looking for is inside the logarithm. If I look on the right side of the equation, this is all just numbers. So go ahead and evaluate whatever's on the right-hand side. The natural log of P2 over this equals, just evaluate everything on the right. Do it with your own numbers. You're going to get a different number than me if you're using different numbers, right? So, but you should get, 2 or 3 or 4 or something. So what do I do now? Let's go off to the side and remind ourselves of something from yesterday. Yesterday, when we first learned logs, we said the log base 10 of 1,000 was equal to 3. Why was it equal to 3? Because you can rewrite that equation as 10, the base, to the power of 3, that answer, has to equal 1,000, the number that was inside the logarithm. So 10 is the base and 10 is the base. To the power of that 3 out front equals the 1,000 inside the logarithm. We're not using the base 10 logarithm. We're using the natural logarithm. What's its base?
E.
So we don't normally write it, but let's write it in there. Put an E in there. That's its base. Natural log is really just log base E. So if 10 to the power of 3 gives me 1,000, what will be true over here by the same logic? E to the power of 2.02 will equal whatever's inside the logarithm. P2 over 9.2 for me. Now I can just multiply both sides by 9.2. How come I couldn't multiply by 9.2 a minute ago, but now I can? Why could I not multiply by 9.2 here? Anybody? The 9.2 here is in the logarithm, right? This is part of the logarithm. This is not the natural log of P2 all divided by 9.2. This is the natural log of P2 over 9.2. So the 9.2 is inside the logarithm also. You couldn't just multiply by 9.2. But now there's no more logarithm. So now P2 is 9.2 times e to the power of 2.02. You look on your calculator, you look at the natural log button, ln. Right above it, it says e to the x. The inverse of natural logarithm is e to the x. So I go 9.2 times second function natural log e to the power of 2.02 equals 69 millimeters mercury. You should get an answer similar. You remember when I estimated it a minute ago, I said it'll be around 70 just by looking at it. Then I got 69. That's pretty good. Maybe you get 68, maybe you get 71, right? But something close to 70 or 69 is what you should get.
I got 3.2 times 10 to the 20.
I think that's a little off.
I agree.
What was your equation right here?
ln is P2 over 4.6.
So the natural log of P2 over 4.6 was equal to, dear God, was equal to what?
Negative
Okay.
432,000.
Stop right there. I said it should give you an answer like 1 or 2 or 3 or 4.
Oh, what it equaled? 45.
45 is not 1 or 2 or 3 or 4, right? When you take e and raise to the power of 45, you're going to get an incredibly large number, aren't you? So your answer is right. Your mistake is in there. So go back to this. Negative, type it in again. Negative, whatever this number was, 40, well, we're all using the same one, negative 43,200 divided by 8.314 times, open a bracket. Did you switch to kelvins in there?
Yep.
So
Because I use 0, so it's just negative 273.
what? You had to have something minus something.
Yeah, I use the temperature 0 degrees Celsius, so it's just negative 273.
So your second one is 273,
Yep.
but what's your first one?
Didn't we all use the same one?
Did you use 318?
Yeah.
Okay, well, I told you to pick your own. Oh, sorry. For this one, we were all doing 445. You're right. So
Oh, I
318,
forgot to do reciprocals.
you forgot reciprocals. Okay. So folks, what's the last question we'll do tomorrow? We just found delta H. Then we found a pressure. What are we going to do tomorrow?
Finding the temperature.
Try to find a temperature.
Exactly. I'm gonna give you a pressure and say, what's the temperature going to be, right? That one will be easier because the temperature is not inside the natural logarithm, right? But the temperature is a reciprocal of temperature, so it's a little bit tricky, but it'll be easier. So that's what we'll do tomorrow. All right, folks, enjoy your day. We will see you tomorrow. That's the last thing we're going to learn in this unit. Okay. Have a good night.
Thank you, you too.